Okay, we're gonna learn significance figure in this lesson. So, significance figure is important in AP exam because you need to review and consistently apply rule for significance figure and avoid rounding off before the final answers, right? This is according to AP exams. Rounding calculation to appropriate significant figure at the end of the problem, and it is important. So, an example of the AP Chemistry scoring guide. 1 point is N for correct numerical answer with the correct number or significance. So this is the rule or scoring guide that determine whether the students get a point or not. Moving on. So why is significance figure important in science field? It is important because it keeps the number accurate given the range, and the last number on the digits of any figure is filled with uncertainty. So let me give you an example. So this is accuracy versus precision. So on the picture here, we have three different dot board, right? The first picture here, it is, let me get the annotation thing out so I can just move it on. Let's see. So the first picture here, right, it is both accurate and precise because they are all hitting at the same place and they are all hitting the bullseyes. So hitting the bullseyes is what make it accurate, and hitting the all the same point is what make it precise. Here, this is poor precision and poor accuracy because it's not together and it doesn't hit the bullseye. Over here, it is poor accuracy because it's missed the bullseye, it's missed the mark, but it has a good precision because all the dots are in the same place. All right, moving on. So this is what we call as accuracy versus precision. All right, so moving on, precisions, how close a set of measurements are to each other, right? Is tell how the measurement is being repeatable. So if you are throwing dart to the board, and if all the points are hitting the same mark on the board, that means you just need to make some adjustment. Now, if you're throwing the dart to the board, and if your dart is all over the place, you have to practice a lot more because you don't know how to aim, right? Okay, so for example here, right, 21.7 centimeter, that's your textbook width, then that 7 is the uncertainty digit because your textbook could be either 21.6 or 21.8 centimeter, or it could be other number, right? So it's 21 point something. All right, let's take a look at the mark again. So we're trying out here. Let me get the straight line mark so that we can draw it up. So if I were to draw it up, I know it's a little bit off, but you can see, right? It is something between the 30 and 35. So what is the length of that blue bar is? So you can make it as an estimate to say you can guess a couple of numbers. So you can say it's 31. You can say it's at 32. Right? You might even say it was 33, although that might be pushing it, probably not. But what you cannot say is, it was 31.5. Okay, so that's something that you cannot say. You cannot say this. You can guess them as is, right? These two is okay. You can go ahead and guess them as is, either 31 or 32. But you cannot guess it as 31.5. Okay. All right, moving on. So let's take a look at that line again. So I'm going to try to draw the line again so we can probably see better. I'm going to try to make it accurately as possible. So you can see here, I just draw the line up and it seemed to be around 31, I would say, right? So I'm not sure. I'm going to try to draw as straight line as possible. Yeah, it's around 31. So again, if we were to make a guess, I can say it's at 31.0, meaning that I am sure it was 31. Or I can say, it's not really 31, it's a little bit less. So I can say 30.9. Okay, so I can make the guess about it. Now, what you cannot say again is you cannot say this as 30.95 or 30.99 or 30.94, whatever it is, right? You cannot say that. This is not allowed to say that because we don't know that it was 30.9. We're just saying that it is around there, right? It is above 30, but it could be around 31, but maybe less than that. So that's what it is. So again, it's just estimations, basically, right? Moving on. Okay, so reading the volume of the liquid. So right now we are doing digitally, we're looking in the pictures. But if you were to look at the water level in a graduated cylinder in class, what it is you always try to level your eyes to where is the lowest, point of the curve of the water, right? You will never ever look at this. This will be wrong. You do not want to do this. You want to look this one. This is a correct one. Okay, this eye is correct. This is wrong. You also don't want to do this. So looking down, looking up, those are all wrong. And you're always looking at the bottom of things. And this is what we call as meniscus. So that's what you want to do whenever you're looking at the liquid volume. All right, so let's try looking at the liquid volume here. Same idea, right? You want to look at eye levels, meniscus, the lowest part, which is right here, right, close enough. So if you go like this, now you notice that it's not that curved. It's a little bit hard to draw a curve on the computer, so it's not really curved, but it is close enough somewhere there, right? So by definitions, if we had to guess again, 15 and 20, so it's between there. So we can count 1, 2, 3, 4, 5. So that means each mark is 1. So that means 15, 16, 17, and then there is 18. So it's between 17 and 18. So I could say it is 17.4. I could say it's 17.5 if you think halfway. And then you're like, no, it's a little bit higher, 17.6. I can say there's 17.7 even. Okay, so I can say all of this. What you cannot say is you cannot say it is 17.55, 17.58, 17.59, right? Because we don't know it was 17.5. We know it's 17 something, okay? So hopefully that makes sense. All right, moving on. In the labs, there are two types of error usually. One of them is called systematically error. So that means you're getting the same result, you're getting precise data, but they are always too high or too low. So usually that happens is because your equipment, the material that you use to measure is not calibrated. So that means like if you're using the balances, right, to measure the mass, maybe the balance is off. So that could be it. And then this type of error usually cannot be corrected by repeated measurements because the error is part of the machine. So you're gonna keep getting the same error. This is where like you get precision, but not accuracy. Random error is a result of all the measurement that are either getting too high or too low. Right, so that could be like you're looking at the water level in the meniscus, and one time you look at it, you look at too high. The next time you look at it, you look at too low, or that could be it. Or maybe sometimes you're measuring things and you're scooping, right? And then you might scoop up too much, too little. So that could be the error. Sometimes it's just a random error, and that could result in the number getting higher or lower. Usually that can be adjusted if you make multiple trials. Because after doing, let's say, 4 or 5 trials, if you take an average, usually that will even out the error. Okay, so human error. So when writing the lab report, you cannot cite human error as a source of error. So if it's human error, you can eliminate it by doing the lab carefully. It has to do with the experimentals, right? How familiar with the experiment that they're doing. Now, if they are spilling chemicals or reading measurement wrong or doing the calculation wrong, right, they can go back and fix it. They have to redo these measurements or the lab or the trial so that they can get a better results. So yes, never really write them as human error. Okay, so vocabulary is the non-zero number. Those are basically the number that are not zero. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Significance figure rule. Okay, so there's 3 rules you have to remember. They all have to do with the non-zero number and the zeros and also decimals. So let's get started. So the thing with it is, I'm gonna start. is never count the zeros in front. Okay, so in the front, zero are never count. So like these, we don't count them, right? These in the zeros in the front are not counted ever. So they are not part of it. Same thing here, these zeros are not gonna be part of it, right? These zero in the front are not gonna be part of it. So never count the zero in the front. And then you always start counting from the non-zero number. So the way that you're gonna do, you're gonna start counting from the non-zero number. So let's go ahead and start it. So let's go ahead and start counting. So that would be 1, 2, 3, 4, right? I have 4 of them. I'm gonna count 1, 2, 3, 4. Now I'm kind of skipping over because I know this rule, rule number 2. Rule number 2 said you count until all the non-zero number are gone. See that how there's a non-zero number here and there's a non-zero number here. So what happened is all the zeros sandwiched in the between are automatically count because there's a non-zero number at the end. Okay, so by that logic, you can also count all of this. 1, 2, 3, 4, 5. So this one would be 5 significance figure. This here is a 4 significance figure. This up here is a 4 significance figure. All right, let's try to count the one on the third one. So for the third one, same thing. Non-zero number count, non-zero number count, all the sandwich also count. So 1, 2, 3, 4. Okay, we have 4 of them. And then same here. 1, 2, 3, 4. Now we kind of get into the little sticky situation, right? So we kind of now has the zeros at the end. We're talking about these. So what do you do with these zeros at the end? So in that case, what you do is you look for the decimal. You look to see if there is a decimal. So for example, this one, there is no decimal to be found, right? The next number, there is a decimal here. If there is a decimal, then what happened is all the number at the back is non-count. So this is non-count. So that means 1, 2, 3, 4, 5. This is 5 significance figure. This one, there is no decimal at all. That means these at the back don't count. So that means I just count the earlier one. 1, 2, 3, 4. 4 significance figure. Okay. So hopefully that makes sense. So this is a significance figure and how to count them. All right, moving on. So these are the answer. All right, there's another method that you can use, something called box and dot method. So let's get started and let's see how they work. So the way that you do box and dot method is this way. You draw the box around all non-zero digits. So that means if there is non-zero, you box them. So that means 2 is a non-zero. So I can start the box here. I keep scanning until all the non-zero are gone. So that means 4 is a non-zero. I can box it, right? So you did see, I just gonna do that. Next is you want to look at it as the next rules. The next rule said if there is a dot present. So dot as in we're talking about decimal. So you can see here there's a dot present, right? So if the dot is present, so that's what they're saying, draw the box around all the tailing zero. Tailing zero are basically 0 at the end. Okay, so that means I can draw it around this guide, right? So I'm just gonna draw it around this guide. So what does that mean? That means now all the box draw are now count. So that means now I'm gonna go and count them. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. So this is a 8 significance figure. Okay, so that's how you have to do them. You just count them according to this. You can use either this method or you can use it according to the rule that we said before. Either one is fine. So that is how you do them. Okay, so let's try to apply them. Let's try to apply them. So you can see, so let's try to apply them. Oh, so we have this question. So how many significance figure it is? Okay, this one is a little bit tricky, but because of you have this, right? You can ignore that. because it is already something called scientific notation, which you're gonna learn in the next lesson. So you can kind of ignore this and then just check. See how there is a decimal? We're just gonna count them all. 1, 2, 3, 4, 5. 5 significance figure. Okay. So yeah, I'll talk about this one in the next lessons. So let's move on. Oops, let me clear that one up. So in the AP test, what is it? Again, I give you another example. So in this case, they try to find the Q, which is a charge, by multiplying, and then they solving this, and then they get the answers, right? So when determining the number significance figure in the answer, we ignore the number electron because this is the exact same number. So again, sometime when you have the exact same number stuff, you will ignore them. So for example, if I were to say $1,000, okay? Now I'm not estimating that I said, oh, it's about $1,000, right? I'm not estimating. I said $1,000, so it's mean it's not $99. I mean $999, or it's not $1,001, right? So it's $1,000. That means all of them are significant. So that I don't. This is called exact significance figure. So technically, what they have is they have infinite number of significance. So you don't use them for the purpose of rounding, okay? Or counting the significance figure, which we'll talk about in the rounding also. So, so in the rounding, what happened is when you see the, like say 100%, you don't round the 100. You don't count it as 100 is one suffix, so therefore you round to one suffix. So not it. Okay. Again, we'll talk about that when we get to the rounding session. So, so hopefully you understand the significance figure. Go ahead and do the practice problem and practice them. And if you have a question, send me a message, and yeah, see you in the next lesson.